Hey folks, welcome to lecture 2-3. We're looking our way through chapter 2, atomic structure, and we've moved on now to electrons. So we're looking at the electron arrangement in an atom and something called valence electrons. All right, so in chemistry, electrons are very important. The physical and chemical properties of an element are largely determined by the electrons, and specifically by the energy of the electrons and the arrangement of the electrons. Now, recall our model of an electron has a nucleus. It's very dense with protons and neutrons and something like around the nucleus would be the electrons. So they make up the volume of an atom. Um, I think we talked about how it was the the nucleus to the atom is like a football to a football stadium, right? So most of this space is determined by where the electrons are. Actually, most of the space is empty, um, which is kind of a weird concept to think about. But the volume is ultimately about the electrons. So they're the ones interacting when you have chemical properties. So we're going to talk about energy and then arrangement. And when we mean arrangement, it's kind of like how do we order and structure the energies of these electrons? So again, we can say that the arrangement of electrons in the atoms determines the physical and chemical properties. And then the electron arrangement is based on theories that came from quantum mechanics. And quantum mechanics from physics tells us that electrons in an atom can only have certain allowed energies. These are known as energy levels. And N is the symbol that we use for allowed energy levels. It's called the quantum number, N. This is a really weird concept, this certain allowed energies thing. So I want to spend a moment talking about that because that's going to be really important. You don't have to understand the quantum mechanics of it or why it's necessarily the case, just that it is the case. So we can think about the energy that an electron possesses as being um, like elevation above ground, right? And so this would be like the lowest energy, and then um, as you go up, like maybe you're going from the first floor of a building up to the roof, right? And so classically, right, you would expect uh, like something more like a ramp, that electrons could have energy anywhere along this continuous continuum, and at any point along the way, you can stop on a ramp, right? And you can have whatever possible height or elevation is at that spot. But quantum mechanics tells us that energy is more like stair steps, right? So there's an allowed possible energy, like being on the first step. There's a possible energy, like being on the second step, but it's not possible to be in between, right? And so, I mean, think about like you can't float between two steps. You have to be on one step or another. And so these steps would be discrete, or we could say they're quantized, as in um, they are separated. And these different levels, or the different steps, these are what we're going to call the energy levels. Okay, so an electron can only have certain allowed energies that correspond to these energy levels, and they're going to be based ultimately with some number n. Okay, so let's talk about what that is and how it relates to the periodic table. So this is pretty simple connection that n is equal to the period. Remember, periods are the numbers of the rows. And so the first row is n equals 1. And so it's energy level 1. This next row is energy level n equals 2. And the next row is energy level n equals 3. And energy increases as we go down or the energy of the electrons that we would be, like looking at in rubidium would be higher energy than sodium. So a higher energy level means higher energy, and it also means uh, that the electron is farther from the nucleus, so it's farther away. Okay, and here's that stair step again. This is a picture from your textbook. So we see that they're actually not even stair steps, right? The distance between the levels, or the difference distance between the steps changes, um, but that's fine. Okay. So here's hydrogen, element number 1, so atomic number 1. Helium is atomic number 2. Lithium is atomic number 3. And we see now uh, energy on the y-axis, and the levels are represented by the lines. So these are the energy levels. And we're going to represent the electron by putting a dot on a certain level. So hydrogen has 1 electron. Hydrogen is up here in energy, or period 1. So n equals 1. There's 1 electron in the n equals 1 energy level, and so we just draw a dot. Now for helium, helium would be over here on the periodic table. If you look at your own, I just didn't have room for the whole thing here. And it's still in it's still in period 1. So its energy level n equals 1. And it has a neutral atom of helium has 2 electrons. So we would just draw them as 2 dots on that line. Okay, now lithium. Lithium comes down here, and it's the first element in row 2. So period 2 means the energy of the outermost electron will be an energy level n equals 2, which is higher than n equals 1. And so it still has atomic number 3. Neutral atom has 3 protons, 3 electrons. We still have 2 in the first energy level, but now that third one would have energy corresponding to energy level n equals 2. And so this is just a little bit of how we draw this. And the difference between valence and inner core will come up in just a few slides. Okay, but here the core concept is that electrons can exist only in allowed energy levels. Okay, this is a result from quantum mechanics, which we will not actually derive, but we'll just use. And we recognize that there's a connection between the periodic table and the periods and these energy levels, which are identified as n equals 1, n equals 2, n equals 3, and so on. The higher values represent electrons with greater energy and more likelihood of being farther from the nucleus. So if you are asked about, an n equals 3 energy level and an n equals 1 energy level, what are some differences? Well, one, is that the n equals 3 energy level is higher energy and farther from the nucleus. Okay. So when we talk about electron arrangement, what we mean is looking at all the electrons in an element, in the atom of an element, and discussing which energy levels they are in. Where are they? Okay. Now, it's true that electrons occupy the lowest energy levels that they can, right? Because nature tends to go towards lower energy, more stable. So the electrons occupy the lowest energy levels that they can. So basically, we fill up energy level 1 before we move on to energy level 2, which fills up before you move on to energy level 3, and so on. But there are actually a maximum number of allowed electrons in each energy level. Okay, and so we're going to talk about what those numbers are, what the maximum numbers are. And so to determine the ground state, which means lowest energy, electron arrangement for the first 3 rows, which would be elements 1 through 18, we're going to fill the energy levels according to these steps. So the first thing we need to do is determine the total number of electrons in the atom. Now, if you know the identity of the atom, you know the atomic number, then you know the number of protons. And then from protons you can get the number of electrons. If it's neutral, then the number of protons equals the number of electrons. If there's a charge, remember last time we said that charge is equal to protons minus electrons. And so the number of electrons would be equal to the number of protons minus the charge. For this chapter, we're going to be dealing with neutral atoms. But if we had charges, we could still do this. Okay, so once we have that determined, then we add electrons to the n equals 1 energy level first, up to a maximum of 2 electrons. Remember we saw hydrogen and then helium, and then when we moved to lithium, it was the next energy level. Okay, so add electrons to the n equals 2 energy level next, up to a maximum of 8. And if you look at the n equals 2 row in the periodic table, there are 8 elements in that row. And so we add 1 for each row, and then when we hit 8, we move to the next row, n equals 3, up to a maximum of 8. Here is a huge table, but it's table 2.5 from your textbook, so you can go and look at it. And after we look at this for a few moments, I'm going to give you an alternate representation. But this gets at what we just described, right? So atomic symbol and atomic number here are going increasing in order. So we start filling in electron arrangements. So we say like hydrogen, it has 1 electron. What is the energy of that electron? Well, that 1 electron is in the n equals 1 energy level. Okay. Helium has 2 protons, 2 electrons. Both those electrons are in the n equals 1 energy level. But if we skip ahead to say carbon, okay, carbon is down here. It's atomic number 6. It has 6 electrons. So the first 2 will be in the n equals 1, and then there will be 3, 4, 5, and 6 total. So 4 in the n equals 2, and none in n equals 3. And so we see we count up 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8. And if we end up with something in the third row, like silicon, which is right below carbon, okay, it will have, of course, 2 in n equals 1, a full shell, as we will say, of n equals 2, and 4 of n equals 3. All right, and so you can kind of look through this whole table and maybe make some sense of it. Notice that these numbers have to add up to the atomic number, right? So here it's 2 plus 4. This one is 2 plus 8 plus 4, and so on. All right, an alternative, we'll end with this, an alternative way of viewing electrons is kind of in orbits around the nucleus. And this representation here shows the energy levels as expanding orbits, okay? And then the dots, again, are the electrons, and here the energy levels are represented by the circles. So hydrogen has 1 electron in the innermost. I like this representation because it also shows that the electrons get farther from the nucleus as you go down. in energy levels. So n equals 1 has one circle and up to 2 electrons on it. N equals 2 adds a second circle around it and adds up to 8 within that circle. And then n equals 3 adds a third circle farther from the nucleus, and it will have 8 around it. And following on in the next row, we get a fourth circle. Okay, so this is again just an alternative way of viewing it, similar to table 2.5, but slightly different. Okay, and in the next video, we will talk about how we differentiate the electrons that are in the outermost ring here, or what we'd also say the highest energy level, and those are called valence electrons, and we'll talk more about those in the next one.